Okay, this problem is related to the conservation of momentum. So let me first make the diagram and then we'll discuss. So there is a small mass m that is moving in this direction. So this is the line of motion. Are you getting? And this collides with a mass m that is kept here, and then this mass moves in this direction, capital mass m with velocity v2, and let us say this mass moves in this direction, a small mass with velocity v1, and this angle is given to you alpha. This angle is also given to you, that is beta. And let us call this direction as a x direction and this direction as a y direction. Now let me read the question. So this says a small mass m moving with velocity v. So this mass is moving with velocity v, collide with another mass capital M that is initially at rest. So there is a mass capital M. This mass is kept here and initially at rest. So this was initially at rest. Now this mass collides with this mass. As the result of collision, m diverges with an angle alpha. So m diverges with an angle alpha from its original direction. So this was the original direction of a small m. Now it is moving in this direction with angle alpha from the horizontal. That is the line of movement in the first case. After the collision, m moves in a direction which makes an angle beta to the original direction. So this is the m. Now this is moving in this direction, that makes angle beta with the original direction. Calculate the velocity v1, v2 and m, v1, v2 of m and m capital respectively. So v1, I have to calculate v1 and v2. So let us say this is v1 and we have to calculate v2. And also what is the ratio between initial and final kinetic energy. So this is the one thing we have to calculate. Another thing we have to calculate initial kinetic energy divided by final kinetic energy. So how will you proceed for this problem? You see, this system is kept on a horizontal, a smooth table. So I can apply the momentum conservation. In horizontal direction there is no force. So if I consider this and this as a system, there is internal forces acting, but no horizontal external force that is acting. So I can say momentum of this system remains conserved. Now momentum conserved, that is P is constant. And now P is a vector. I can also write Pxi plus P by Z because P is a vector, momentum is a vector. Now this is constant. This means I component and J component can separately be also constant. So now I can apply momentum conservation along the x direction. I can also apply momentum conservation along the y direction. So this is a two-dimensional momentum conservation equation. So if I write momentum conservation in the x direction, what is the initial momentum? Initial momentum is mv. What is the final momentum? Initially this was raised to momentum of this is 0. So if you want, you can write m into v, and that v is 0 basically. So momentum is 0. So initially this is 0 velocity. So this is 0 plus mv. Now what is the momentum? mv1 cos alpha in this direction. So we will have a small mv1 cos alpha. And this will have cos beta. So mv2 cos beta. So if you write this equation, you will have mv is equals to mv1 cos alpha plus mv2 cos beta. Are you getting? So this is my in x direction, momentum conservation in x direction. Let us write momentum conservation in y direction. So if I write momentum conservation in y direction, initially there was no momentum in the y direction. This is moving in the x direction. So initial momentum in the y direction is 0. Finally, this has a momentum in negative y direction, that is y1 sin alpha. So minus m1 v1 sin alpha, that is in the downward direction. And the top one will have momentum in the upward direction. So m into v2, and this is sin beta. Are you getting? So we have two equations. Equation number 1 is this. Equation number 2 is this. We can solve for V1 and V2. I am giving you the final answer. After this video, you check your answer. So this answer comes out to be, I'm not going to solve this equation. So V1 and V2 I'm writing. You have to solve yourself. So V1 comes out to be sine beta divided by sine alpha plus beta into V. Similarly, V2 will be sine alpha divided by sine alpha plus beta MB divided by capital M. So this is the value we'll get for V2. So you check your answer. Similarly, final kinetic energy divided by initial kinetic energy, that is basically final kinetic energy is capital mass M, is now moving with velocity V2 square. A small mass M that is moving with velocity V1 square, and initially only this mass is moving, so first mass, that is half mv square, you have half mv square. So this is the initial velocity, and if you take this ratio, I am giving the answer, you have to calculate it yourself. M, because V1 V2 you know, M sine square beta plus a small m sine square alpha plus m sine square alpha, and this divided by m sine square alpha plus beta, m sine square alpha plus beta. So you have to solve yourself. Are you getting or not? That is important part. So you will have here 2. So let us solve yourself and then go for the next video. So try to solve these equations. So very easy. You have to write in this case equation of motion in 2 dimensions, in 2 directions. Momentum conservation will be applied in x direction as well as in the y direction. Initial momentum of the bigger mass capital M, that is 0 because it was initially at rest. So in the x direction, a small m into v is equals to m v1 cos alpha, because in the x direction velocity component for this is cos alpha, for this is v2 cos alpha, both are in the positive x direction. For y direction, this will have a v1 sin alpha, that is in negative y. This will be v1 sin beta, that is the positive y. So if you apply momentum conservation, you will find what is the final velocities. You can also find out the ratio of kinetic energy. That is a very important point. Whenever you have a collision, we generally find what is the loss of kinetic energy. So what is the ratio of final kinetic energy to initial kinetic energy? Let us discuss the next problem. This is a quite easy problem. You have to solve yourself.